Welcome to this explainer. Today we're tackling, and I mean quite literally, the absolute biggest mystery in modern science. We are going to dive deep, deep down into the microscopic foundation of the universe to explore Dr. Ahmad Rihan's new parallel alive physics. It's a wildly fascinating framework, and honestly, it might just be the ultimate key to unifying everything we know about reality. But before we get into the heavy stuff, I want you to do something for me. Just look around the room you're sitting in right now. Look at the space between you and your screen. It looks completely, perfectly empty, right? A silent, invisible void. Well, what if that seemingly empty space is actually a bouncy, dynamic, living structure? What if the universe is, at its most fundamental microscopic level, a sponge? Here is our flight path today. We'll start with number 1, the crisis in modern physics. Then 2, the spongy spacetime hypothesis. 3, the electromagnetic master force. 4, how gravity actually emerges. And finally, 5, testing the living fabric. We're going to zoom all the way down to the smallest pieces of the universe and build reality back up together. Let's get started. Section 1, the crisis in modern physics. So, for nearly a century now, our understanding of the universe has been fundamentally, broken. We have these two incredibly successful ways of describing reality, but when we put them in the same room together, they just completely refuse to cooperate. General relativity treats gravity as this perfectly smooth, continuous mathematical sheet. It is absolutely phenomenal at describing the massive, sweeping movements of planets and galaxies. On the flip side, we have quantum field theory, which excels at describing the fundamental forces of the microscopic world. But it assumes reality is fundamentally discrete, broken up into tiny quantum chunks. One is smooth, the other is chunky. And this brilliantly illustrates the problem. When physicists try to force these two uncooperative prime suspects together to quantize gravity, the math just explodes. It literally spits out infinite divergences. We desperately need a unifying theory.
Moving right along to Section 2, the spongy space-time hypothesis.
Okay, it's time to put on our microscopic lenses. We're zooming all the way in to the absolute limits of the quantum world to look at Dr. Rihan's radical solution. Imagine space-time isn't that smooth sheet of rubber they taught us about in high school. Actually, scratch that. It's inherently discrete. In this model, space-time is a lattice of deformable, Planck-sized cellular units. Think of them as these tiny, energetic little building blocks that can bounce, stretch, compress, twist, and even change shape from cubic to spherical when they're under stress. Essentially, space-time is bumpy. It has texture.
To quote the source material directly here, this framework envisions reality as a discrete, porous, cellular medium at the Planck scale. Now, why does this matter so much? Because this exact physical sponginess provides what physicists call a natural ultraviolet cutoff. Remember those crazy mathematical infinities I just mentioned that plague quantum gravity? Well, this physical limitation, this porous cellular boundary, it naturally tames those mathematical divergences. It finally allows the math of the very big and the very small to speak the exact same language.
Section 3, the electromagnetic master force. Prepare yourselves for a massive paradigm shift. What if I told you that out of the 4 fundamental forces in the universe, only one is actually fundamental? Okay, let's dive into this. The absolute core innovation of this entire hypothesis is the MEE framework. That stands for macro electromagnetic emergence. The radical idea here is that gravity, the strong nuclear force, and the weak nuclear force, they're all just macroscopic illusions. In reality, all physical interactions originate from electromagnetic-like fields and charges operating right down there at that tiny, spongy cell level. Every force you know is really just a different mask worn by electromagnetism. No way, right? But the framework backs it up. Let's walk through this 1, 2, 3 zoom-out progression to demystify exactly how different forces are just different scales of the same underlying electromagnetic dynamics. Step 1, at the absolute shortest range, high-energy electromagnetic interactions confine and bind together in tight, flux tube-like deformations that perfectly mimic the strong force. Step 2, as we zoom out to an intermediate scale, symmetry breaking yields behaviors that we experience as the weak force. And finally, step 3, at the grand, macroscopic scale, the averaged, residual effects of all this microscopic EM activity produce what we know and feel as gravity. Which perfectly tees up Section 4, how gravity actually emerges. So how exactly does this microscopic, bouncy lattice build the massive gravitational forces that hold our actual planets together. Now, what's really interesting about this slide is how it grounds the complex math into a very tangible, undergraduate level analogy. Just picture spacetime as a vast 3D array of springs and electromagnetic charges. When you introduce mass or energy into this environment, it literally displaces these charges. Because of that, the springs stretch, but asymmetrically. In this asymmetric stretching, it creates a net attraction across the whole lattice. It's just a beautifully tactile, mechanical way to wrap your head around gravity.
And this answers one of the most famous, nagging questions in physics. Why is gravity so incredibly weak compared to, say, a simple refrigerator magnet? Well, in this framework, it's because gravity is simply a higher-order collective residue of those microscopic EM energy densities. So instead of a planet just mysteriously falling toward the sun, large concentrations of mass are actually physically compressing those radial spongy cells around them. That compression creates cascading potential wells in the lattice itself, and the absolute beauty of this whole thing is that the math actually works out. Now, without getting bogged down in the complex calculations, the source material shows that Dr. Rihan's single unifying equation successfully proves consistency across the entire board. From just this one MOE equation, you can derive everyday Newtonian gravity, the general relativistic metrics we need to understand black holes, like the Schwarzschild metric, and even highly specific quantum gravitational effects, like Hawking radiation. It elegantly bridges the gaps that have literally stumped the greatest physicists for decades. Section 5. Testing the living fabric. Now, a theory is ultimately only as good as its proof, right? So let's talk about the real-world future of this hypothesis and how scientists can actually prove it. Because this framework bridges solid-state physics intuitions with quantum gravity. It doesn't just sit on a chalkboard as pure, untestable mathematical philosophy. It practically begs for formal empirical scrutiny. Scientists can look for real proof through high-precision gravity measurements or by hunting for specific cosmic ray dispersion anomalies that a spongy lattice would predictably cause. They can even build analog lattice simulations right here in the lab to see if the macroscopic behaviors match up with the theory. We are looking at, to quote the abstract directly here, a promising avenue toward a final theory rooted in a dynamic, living fabric of reality. Just let that sink in for a second. This hypothesis completely, fundamentally redefines the very fabric of our universe. It takes space-time from being this sterile, empty mathematical vacuum and transforms it into an energetic, breathing, living tapestry. So as we wrap up this explainer today, I want to pose that exact same question to you that we started with. Look around the room one more time. Stare right into that empty space in front of you. Based on what we've just uncovered, is that space truly empty, or is it alive? Thank you so much for letting me guide you through this mind-bending material today. Keep questioning the world around you, and I'll catch you in the next explainer.